Okay, so now we have to be live on YouTube as well. And hello, everybody. And my name is Olgunaydın. I'm an active member of IR Foundation. Today, it's a great pleasure for me to be chair of this session. And we have extremely great speakers and very exciting topics. And I'm already excited and I cannot wait. And I don't want to take your time. And because, like I said, there are very exciting topics to hear. So our first speaker on this session will be Jeremiah Reyes. So he will be talking about agent-based modeling with goal-oriented action planning and RCPP. Okay, Jeremiah, it's over to you. Wish you good luck.
Okay, great. Thank you. So I'm Jeremiah. I'm very glad to be here. I'm affiliated with the Leuphana Universität Lüneburg in Germany. And I'm really happy to share my research with fellow R lovers. And the title of my presentation is Agent-Based Modeling with Data.Table and RCPP. I won't assume any background knowledge. So I'm going to introduce these concepts to you. So I'm going to talk about agent-based modeling, or ABM. And I'm going to talk about the AI that I'm really looking into, called goal-oriented action planning. And finally, at the end, I'm just going to state why I think data.table and RCPP are an ideal combination to use for this kind of project. So in a nutshell, agent-based modeling is all about simulating independent agents interacting with each other and or the environment. And normally when there are introductions to agent-based modeling, people always mention the work of Thomas Schelling and his so-called segregation model. Thomas Schelling was an economist, an American economist, and in the 1970s, he created this model that looked into the racial segregation of neighborhoods in the United States. And basically, he came up with this, it was just a checkerboard. He did this manually at the very start. A checkerboard filled up with agents of two different colors. And each agent followed a very simple rule. So I paraphrase this rule here. The rule is, if at least X% of my neighbors are the same color as myself, I will be satisfied and stay in place. Otherwise, I will move to a different location. So it's a rule, it's a desire for similarity amongst your neighbors. And here is an implementation of this model in NetLogo, which is the most popular software for ABM right now. And you see at the left top side, the threshold value of, let's say, 30%. So agents will be happy if they have 30% similar neighbors. And if they're not happy, then they will move to a different place. We also see 2,000 agents here of two different colors, green and red. And if you let this model run, okay, agents will keep moving until they are all satisfied, and you end up with this result where you see some kind of segregation in the neighborhoods. Now, if you raise the threshold value to something like 65% and you run this same simulation, then you will end up with even more prominent segregation between these neighborhoods. So what's interesting about Schelling's segregation model is that he showed that there was you just needed one rule to cause the segregated neighborhoods, and you didn't actually need a negative discriminating rule that says, for example, if X% of my neighbors are of the opposite color, I will leave. Okay, the one rule, the desire for similarity, is sufficient to cause the segregated neighborhoods. And of course, this sparked a lot of debate and controversy. I mean, people, of course, believe is involved in the real world when it comes to segregated neighborhoods. But Schelling showed that even if you didn't have that, if you had just the positive rule, these segregated neighborhoods could arise. And this was a milestone in agent-based modeling, and a lot of people really look back to this model as one of the foundations for the field. So you can have simple models like Schelling's model, and you can go to very, very complex models. So here, for example, is a model, agent-based model that attempts to simulate the entire European economy called EURES, a very interesting model and very complicated. This is their schema that you find on their website. So you have many institutions, many markets, and of course, more complex agents than what you find in Schelling. Agent-based modeling is characterized by independent behaviors of agents. So each agent has to have its own actions. Heterogeneity, agents can be different from each other. And perhaps the most interesting is the concept of emergence, where the micro behaviors of agents can result in large macro patterns that you cannot really predict from the micro behaviors alone. Swarming and flocking behaviors are a perfect example of that. Birds in a flock, they do not talk to each other to move the whole flock this way or that. They just follow very simple rules, but the end result is what you might even imagine is an intelligent collective moving in sync. Now, the most popular ABM software right now is NetLogo, which I just showed, followed by a couple of Java softwares and libraries. And there's also a Python, a more recent Python package for agent-based modeling. We do have ABM packages in R. They are not as popular, but they are also interesting. Spades is one of them. This is primarily used for ecological simulations. We also have RNetLogo, which is not pure R, it's an interface, R interface to NetLogo. So you have to have NetLogo and R open at the same time. And then more recently, we also have NetLogo R, which is trying to replicate the whole NetLogo framework in R. And I think that's also worth looking into. However, yeah, for my purposes, these packages were not enough because I'm looking into a particular AI called goal-oriented action planning. Now, in Schelling's model, the agents were guided by a very, very simple rule. But you can have even more elaborate control mechanisms for agents. And sometimes these are called cognitive architectures. So depending on maybe your own theory of how the human mind works and depending on the goals of your model, you can have a complex, complex code, complex behavior for each agent in the model. In ABM, there are already a couple of established cognitive architectures, and these are some of them. But I looked into these architectures, and actually I found more inspiration from AI in computer games. And so this GOAP that I'm talking about originated from computer games. And it has been successfully implemented in a couple of commercial computer games, such as Fear, Shadow of Mordor, and Tomb Raider. And this was developed in 2003 as an improvement over the more common kind of AI that you find in computer games called finite state machines. And I'll explain why it's supposed to be an improvement. But recently, some people in the agent-based modeling field are starting to take notice. So in 2018, we find the first published ABM using GOAP in their agent-based model. So GOAP is supposed to be an improvement over FSMs. And in a finite state machine, you have a finite number of states that an agent can have. And you also have transitions between those states that you need to program. Okay, so here's an example of that. So you have to program the states, and you have to program also when states transition from one state to another. And this is fine when you have just a handful of states, like in this example, but it can become quickly very entangled if you have many states and many transitions and transitions between transitions, okay, and so forth. So what GOAP does is that it decouples all these states and removes all the transitions and makes them, you could say, free-floating states or actions. And given a certain goal, GOAP will find the path from the starting state of the agent to the goal state using the most cost-effective sequence of actions. So this is obviously a game example. Okay, so the agent draws weapon, reloads weapon, attacks, and kills the enemy. So you don't have to program the path or the transitions in advance. The algorithm will do it for you. Okay, so the agent will have goals. The agent will have a list of possible actions, and at each turn, an agent chooses the most cost-effective sequence of actions that will lead to its goal. And this last part is actually the most interesting part here. It's because the last part uses the A-star pathfinding algorithm. Here we have the same algorithm with different parameters, and it's used to help characters in a game to move from one place to another and avoid obstacles along the way. So it calculates the best path. Okay, so it was originally meant to find a path, and move through obstacles. But what Jeff Orkin did was to take that algorithm and then use it in this space of possible actions and find the best path amongst those possible actions to reach a certain goal. And I think that's really a genius move. Of course, you can already imagine that this is not free. This can get computationally expensive, especially if you have a lot of possible actions and if you have a lot of agents in your simulation. And this is where data.table and RCPP come into play, because these packages are two of the fastest packages we have in R. And I think they really have a lot of potential in just creating these ABMs with goal-oriented action planning. Data.table takes care of course, all of the data. It has very fast data access, data manipulation. And in the schema that I propose, you can have just 4 massive data tables, okay? A data table for objects, all the objects in the world with their attributes, a data table for all the agents in the world and their attributes, okay? And by attributes of agents, I mean things like skills, knowledge, goals, possessions, what have you, depending on your simulation. Also a data table for all the possible actions that you can have, that agents can choose from in your model. And last but not least, a data table for the whole history of your model. So after every turn, you copy your objects and agents into your history data table. And so that can be, at the end of it, a very, very huge data table, depending again on your model. So with just these 4 data tables, I think you can already create a very impressive agent-based model. Here's an example of an object data table. It's a very, very simple example. So you have different objects, their types, and certain attributes that they have. And then here's an example of a agent data table. So if the objects data tables are wide, the Agent data tables would probably be a bit longer, okay, because you have a lot of different kinds of attributes that agents can gain, improve, or even lose. So knowledge, ownership, goals, skills, and so forth. So data.table allows us to speedily access and manipulate large amounts of data for objects, agents, history, actions. Meanwhile, RCPP allows us to take agent data and all other data and efficiently apply goal-oriented action planning. Okay? And so this is an example of how that would work. So you have a call by data table, and you pass it on to an RCPP function, the whole data frame there, and then that's where you chop it up. And this is the starting code where RCPP starts looking for the goals of the agents, and then you manipulate it further, and then you apply goal-oriented action planning. So that's just the tip of the iceberg, but I'm very happy to share this with you, and I hope you all have a great day. Thank you.
Perfect, Jeremiah. Thanks a lot for this great. Thanks a lot for this great presentation. So let's move on with our next speech, which will be given by Maria Kubara, and the topic will be multithreading computing in R. Maria, it's over to you. Good luck.
Yeah, thank you. So, hello, I'm Maria Kubara from the Faculty of Economic Sciences in University of Warsaw. I'm a PhD student, and today I will show you a topic that occurred to me while doing my master thesis. I was doing a lot of simulations that took a lot of time in R. They were spatial, so even more complicated than the normal data tables. And I was looking for a way to actually make my R run faster. And today I will show you very simple medicine with which you can actually make your code faster and more efficient without getting too much into very modifications of your own code. Of course, as every medicine, it comes with a little note that it needs to be a specific task, and the packages you are using should be okay with that. But I will show you later how simple is that, and probably you could use it in your own work. So this is where the inspiration came from. So I was using my R doing my simulations, and I've looked into the task manager to see actually what my computer is doing. And this is what came into place. So this is the space of my RAM usage that actually it took to make my calculations. And the rest of it is just wasted potential. This is not the optimal way. So you are wasting a lot of time and resources actually just waiting for the rest of the code to be executed. So in here, I will show you how to move from this standard workflow to this actually speed up. This is the same task done with just 3 lines of code more. And as you can see, this uses optimally your resources and shorten the time that you are using to calculate things. So today I will show you 3 main points. So I will show you what is multithreading with a very brief introduction. I won't go into too many technical details. You can always Google that. But I will show you how simple is that actually, what task you can optimize, and how to do it in R with minimum effort. So from the theoretical point of view, in your working machine, you have the most important part, like the heart of your computer, which is a processor, of course. Traditionally, the processor had 1 core, so you just started doing something. It has only 1 slot for calculations. But nowadays, you have more and more cores that can actually do things separately, independent from each other. And the even more news came when we started introducing more processors into one working machine. So even in your laptop, you can have more processors and more cores. And what R is doing, it's using only one of these to run all your simulations. So as you can see, there is a lot of room for you to make it more efficient. And this is the thing that we are targeting to use all the potential. So this means that you are changing your workflow from this top image, right, to the sequential execution of each task on one CPU to the parallel one. So then you, of course, need to have some overhead that your computer will use the space to divide tasks and prepare environment. But then all the tasks will be done independently, and you will, of course, have some less time to do the same thing. So what is about the R? Is it actually a bad programming language that uses only one core? Well, not really. Most of the programming language are doing that. This was a valid assumption in the past, and also there are many issues that come with multi-core computing. There are a lot of technical problems with communications and sharing the data. So mostly it's up to the advanced user to implement parallel computing. So there are two things that you need to have in mind while changing your workflow. So you need to have specific tasks. They need to be independent. As I was showing before, they need to be to be done parallelly. They need to have separate spaces, right? So they need to be independent from one another. Of course, there is also the other thing, which is about the RAM usage. Us, our users, need to be very cautious about that, because when you are using multiple cores, it's like opening few R sessions. So if you are doing some calculation in each one of them, you need to, of course, load the packages and the data into each one of them individually. And if you are forcing your R to use multi-core, then the R will do it in the background. So you need to be cautious about that. And if you have a lot of data or a lot of packages, take that in mind if that won't use up all your RAM space, right? But in most cases, that won't be that difficult issue. And with modern computers and moderate tasks, it will be all right. But you need to check it. So about the workflow. As you can see, you have the toy example with some research project, right? So you just start with pre-processing data, then dividing into the subsamples, which you are doing basically the same thing all over again, but with different subsamples. Then you aggregate them and get the final outcome. So as you can see, this is the repetitive task in the middle that could actually be transformed to the parallel computing. Here you have only 3 slots for that, but imagine that you have 100 different data sets and you are waiting for a computer to do each one sequentially, right? One after another. If you can speed up, you will save a lot of time. So to do it in R, there are 3 basic ways to do that. I will focus on the first one because it's the easiest one with just a few lines of code added. But remember that when you are using, for example, apply, you just change the function, load different package at the lines that I will show you, and this will also be okay. There's also a third way with make cluster and cluster apply, which is more professional way. And it gives more technical issues, but this is a very good way if you are trying to use some remote machines to speed up your work. So you can always look up for that. So let's go to the code because I would like you to have some practical examples. So this is a classic Newell-Davis experiment. So as you know it, or probably, it basically comes down to 2 things, right? So we are generating data sets, 2 independent random walks, do regression, and then have the results and draw conclusions from that. But because this is a research project, you need to do this many times. In a for loop, I have taken the individual task in here, in the center part, and you need to initiate the loop, the matrix that will store your all results. You need to save it every time, and then you have your outcome. So to take the step towards the parallel computing, you need to change your for loop, traditional, to the do loop from the for each package. It's not that much different. You just have slightly different call of the for loop in here. Basically, it does the same thing. Just the one thing to remember is that you don't need to have this matrix that we had before that stores all the results for each package. Will do this for you. You just need to specify how do you want to combine your results, and the last line of your loop will have the vector that would be then combined. And going from that, you just change do for the do par, and that will be made on your more cores. Of course, you need to specify that and tell the R to use all your computer space. So you just need to use the function detect cores to know how many of them do you have, how many can be used. I will do it automatically. Then you register your cores, and then stop them when you are done to go back to the single core R. So let's now talk the efficiency. So as you can see, I was doing this experiment on 2 computers. One is my old laptop that has only 4 cores. It's probably 7 years old. And as you can see, the speed up is pretty impressive, right? So going from the for loop to the parallel loop with just a few lines of codes added, you have 2 times faster execution. I have also checked how this will work on more modern computer with 12 cores and 30 gigabytes of RAM, which is basically my husband's gaming machine. And as you can see, the difference between these 2 machines that are very different in their technology in the for loop is just 2 times, right? So it's not that much. If you are changing your machine, you are expecting it to be more efficient. But because of the single core usage, there's not that much that R can do. So if you want to use up your full machine and the computer power you actually have, you need to switch to more parallel computing. And then you have the 4 times speed up on the better machine. I will also show you the basic experiment where the whole story started. So I am doing a lot of spatial analysis, and I had to generate a lot of spatial data sets and run different models on it. So in this example, I will show you that I was generating clusters in the Lubelski voivodeship. So I was drawing 10 points in the space, then drawing some points around each one of them to simulate cities, and then run models with different k nearest neighbors in which each one of them that was taken into the weighting matrix in the spatial model. So this is the code. The basic, that is a pseudocode for my research project. I didn't do any more of differences in here. The only thing that I did to transform it to the multicore was to change this line of code, right? So I changed the for loop that was going through the different data sets to the for each do par loop. And as you can see, there is one novelty. I needed to load all the packages because it's the spatial data sets and spatial analysis. You need to have pretty much of these. But if you are specifying this to R, it will be done automatically then, right? So about the efficiency about that, this is only a part of my research project, so only one type of data sets that I was generating. And this is the time that it took to just do this small portion of my research normally. Then when I was just using different loop with the parallel computing, the speed up is massive, right? So basically, while changing from my old computer and my single core R to the better machine with the parallel computing, you have to change from a tea break on just a small portion of your research to just quick email box check while waiting for your R to finish. So I think for me as a researcher that does a lot of Monte Carlo and bootstrapping simulations to be a very good way to speed up some things, because sometimes, believe me, it's not about the minutes that you are actually saving. Remember, if you would do some things that are taking 2 hours and then changing it to just like 15 minutes, right? There's also another thing that you need to have in mind, that this is the overhead of the time that you are actually having while changing to the parallel computing. As you can see, the second laptop that I was using, it was 12 core, and the speed up was only 4 times. Why is that? Because of the loading of packages that takes some time. But again, if you have a lot of repetitive tasks, there is also a good way to check if parallel computing is a good thing for you. And that would be all. Thank you for listening.
Perfect. Thank you, Maria, for this great speech. I think this was quite impressive, and how much time you saved by parallelizing your R code. Perfect. Okay, so let's move on to our next speech. And our next speaker will be Jadwiga Słowik, and she's going to talk about where RCPP wins and where it fails, the light and dark side of R and RCPP integration. Jadwiga, stage is yours. Good luck. You are muted, I guess.
Okay, do you see my screen?
Yes, and we can hear you as well. Perfect.
My name is Jadwiga, and before I start, I would like to introduce myself. I'm passionate about programming since I was a child, and I have a strong algorithmic background. I used to start in a lot of programming competitions, and additionally, I have a commercial software engineering background. I can write in many languages, both low level and high level, and last but not least, I am a data science master student at Warsaw University of Technology. Let's look at these two languages, R and C++. The most important takeaway from this table is that R and C++ are totally different. These languages are totally different in many cases. First, R is single-threaded, C++ is multi-threaded, R is high level, is very convenient to use. We have a lot of useful packages which we can integrate, whereas C++ is rather lower level. However, it is efficient because it allows us to make some low-level optimizations. So we would like to develop a project, but which one to use? We have on one side efficiency, on the other side the convenience, but we are afraid. We are afraid of the first situation when the computations takes too long. And we are afraid on the second situation when we decided to use some low-level language and, for example, we are not experts in it, and the maintenance of such projects would be hard. So which one should we choose? Well, we shouldn't choose one. We should choose both and integrate them. And there is an RCPP package which can help us with this. It is a package which is a R API wrapper, and it provides C++ structures for R types, and it makes a C++ function accessible in R. And what is the most important thing, it does not copy object during the invocation of the C++ from the R code. But let's look at the example. We will write our C++ code. Well, the results are awesome. We have better speed, and indeed it was worth it. But it is just enough to write C++ code and export it to R? Well, not really. Not only do we have to have good tools, but also we need to know how to use them. If we use bad algorithm, the writing of C++ code won't help us. For example, in this example, we write in C++ linear search, whereas in R binary search. So where is it worth using RCPP? In for loops that cannot be vectorized, for example, in computation of Fibonacci sequence, but not only, generally for dynamic programming algorithm, it would be useful. The second one, when we need to use some advanced data structures, trees, views, sets, we have a standard template library, we have Boost library, we have some third-party library which we can integrate in C++ and achieve good performance. Third aspect is recursive function and calling functions many times. Calling functions in C++ is much faster. And the last, we should write algorithms that modify inner memory a lot, because in C++ we do not copy our memory, and this is more performant. However, RCPP has some disadvantages as well, and we need to be aware of them in order to create robust code. Let's look at these two code snippets. They look pretty the same. There is a for loop. Inside we allocate some object. However, in the first example, we allocate pure C++ object, whereas in the second example, we allocate RCPP object. What should we tell about the deallocation of this object? Well, in C++ way, the object should be deallocated and the inner memory should be released when the variable runs out of the scope. So after each loop iteration, and it happens for the first example, but it does not happen in the second example. This memory isn't released. But why? Why is it so? These code snippets are pretty the same. Well, let's look at the details in order to understand it. Indeed, in both cases, in each iteration, the structure of a current object is invoked. However, the behavior of the destructor of an RCPP is completely different. In fact, it does not release the inner memory immediately. Well, it just calls the destructor of the RCPP destructor just calls our memory management, and that's it. And the R garbage collector can be called only after the invocation of our API method. So for example, if we go next and we allocate a lot of memory, but this memory is not related to RCPP, it is related to pure C++, then the garbage collector for this previously allocated RCPP objects won't be called. So we can easily run out of the memory. What is the solution? Generally, the solution is that we should not create RCPP objects if we do not want to return them back. And there is an issue on RCPP GitHub repo, and there is a long discussion about it, and I highly recommend to read about it. The second thing, there is an inconsistency in copy constructors. The first snippet is related to pure C++, and we have here a copy. So if we modify V, the W won't be changed. However, in the second example, which is very similar, there's just another data structure, but this is the vector as well. The copy is not performed. So when we modify V, the W would be modified as well. The second inconsistency. Let us suppose that we have a variable which has one attribute, velocity, and we do not have more attributes whose name starts with V. This code in R is valid. However, in RCPP, we will get no. We have to provide full names in RCPP. What are the disadvantages of strongly typed language like C++? The much more discipline and focus is required. And even if the algorithm is the same, but we have to support many types of matrices, for example, integer matrices, numeric matrices, string matrices. We need to support all of the types separately. It means that we have to export another function, the dedicated function. However, we can make some abstractions of the common code, for example, using C++ templates. But we have to be aware that a C++ template is a double-edged sword. It is very error-prone, and we should be very focused when we create such structures, because the errors which we can get are not very descriptive, and the bug is really hard to detect. Well, let's look at this. What should this code return? Well, logically, it should be 5, the vector of one element. Well, that's not true, because in C++, the constructor integer vector is not explicit. So here the implicit conversion are allowed. Let's move on to multi-threaded environment. RCPP parallel allows for multi-threading, despite the fact that R is not multi-threaded. And because of that, calling any function from R is forbidden in multi-threaded environment. In particular, we can't create any RCPP object. But what about this one? We just index, we just get some created previously memory and just want this memory to operate on it. It seems pretty good, but no, it's not thread safe. And additionally, the bugs are very random and errors occurs in a random way. So it is really hard to detect in multi-threaded environment that this expression is not valid. Well, but why? Why does happen? In order to understand it, let's look in details. And RCPP indexing entails the creation of a new proxy over. So there is a creation. So there's a call to our API. And the solution is to use the dedicated R vector and R matrix provided by RCPP parallel. However, the string vector and string matrix is not supported yet. Because the representation of the string vector is much more complex than the other structures, but it does not mean that it can't be done. Just nobody has implemented it yet. So now the additional cost is required. So we need to convert our memory to operate on strings in parallel. It's not very convenient and efficient. Let's move on to choosing the perfect ID. In order to develop our project well, we need to have good tools. And in fact, RStudio is pretty good for developing R packages. However, there is a very little support for C++ programmers. In particular, we do not have extended C++ code completion. We do not have refactoring, and we do not have debugging of our C++ code. So we need to find something different, because we do not want to be like this person. We would like to develop our code in a robust way. So the JetBrains team starts supporting R in the tools. And the current state of the art is the CLion supports building an R package. We need just to install an additional plugin for IntelliJ, but there is still a problem with debugging. We just can build our package and test it. And my solution is that we can apply object-oriented design principles in order to make some abstractions, some contract. For example, for integer vector, the contract would be that we can index it, we can get the length of it for all, and we do some wrappers for all our CPP structures. And in order to debug our code in C++, we put pure C++ objects, and we can test it and run it in IntelliJ. Whereas when we want to build a R package, we just have to swap these objects to RCPP counterparts, and it would be okay. Well, but recently a new solution has been emerged, and it is very promising. I have tested it, and it works on Linux. We can debug our code using Visual Studio Code, and there is public repo in which we can download and check. However, the support of the presentation of some RCPP vectors or other internals is very limited. However, the debug mode works, and we can line by line check what happens in our code. So I highly recommend you this solution. Let's move to the conclusions. Firstly, profile your code and rewrite only bottlenecks in C++. Premature optimization is the root of all evil. Really, we do not have to write all of the C++ code. We have to profile it and find the bottlenecks, because the maintenance of complex C++ code would be too high comparing to the achievement of efficiency. The second one, calling R API code in the multi-threaded environment is not allowed. And do not create RCPP objects that will be returned to R. and try another IDEs, rely on Visual Studio Code, Visual Studio Code particularly, to develop your C++ code, because the support from RStudio is very limited for C++ code. And be aware that RCPP object behavior is totally different than for pure C++ objects. There is a very huge inconsistency. And thanks for your attention. There's the contact for me on Twitter and GitHub, and special thanks to the research group with whom I have the pleasure to work with. Thank you very much.
Perfect. Yeah, thanks a lot for this great presentation, and it looked extremely, exciting and impressive. Okay. So with this presentation, we already completed this section related to high performance computing. We had great 3 talks, and now let's move on to Explainable AI section. And our first speaker in this section, actually our speakers, will be Szymon Maksymiak and Alicja Gosiewska, and they will be talking about practical landscape of explainable machine learning in AI. All right, stage is yours. Good luck.
Okay, so can you see my screen?
Yes, exactly.
Oh, okay, great. So today, my name is Alicja Gosiewska, and today with Szymon Maksymiuk, we will show you new trends in explainable artificial intelligence for R. As XAI is a rapidly developing area, there is no unified taxonomy. So we start with a classification of explanations that we find most relevant, and then we'll show you hot 5 new R packages that you might want to be try out. Okay, but first a little about us. So together with Szymon, we work at MI2 Data Lab, which is a research group at Warsaw University of Technology, led by Professor Przemysław Wiecek. And we are interested mostly in explainable artificial intelligence. And I, Szymon, and Professor Wiecek, during last few months, we analyzed and tried out almost all or even all R packages that may be used to explain machine learning models. And today we would like to share with you some of our findings in this area. But to start from the beginning, short introduction about explainable artificial intelligence. So let's suppose we have some input data, like, for example, that might be a customer information, customer of a bank. And we would like to predict whether we should give or deny a credit for such customer. So a classical machine learning problem, we can use any model, for example, neural network or XGBoost, but such models have some strong disadvantage, especially in such regulated areas like credit scoring, because they are really complex and opaque. And if our client will ask if he or she, why he or she did not receive a loan, we would not be able to answer this question. Yeah, so one way, the old one, but not a bad one, is to use an interpretable model, like, for example, linear regression or a tree, where we can look on the model and explain why the model did some prediction. But the other way might be still using such complex models, but explaining them with explainable artificial intelligence, XAI. And now we'll talk more about this second XAI way. So in the literature, you can find many different categorizations of model explanation methods. Together with Szymon, we summarize them in the form of a map. And I would like to show you this map right now. So first group are methods that are interpretable by design. So they are linear models or trees. The architecture of such predictive models allows us to explain that directly a certain aspect of the model. So for example, for linear models, we may look at coefficients and see what's the importance of different variables. Another group, the second one, are model-specific explanations. These are methods that allows us to extract knowledge for from a specific classes of models. So for example, in neural networks, we can look at the gradients and see which variables were the most important for the prediction. And the third one, the most exciting one, is the group of model agnostic explanations. So these explanations analyze the model without any knowledge of the internal structure of such model. So they can be carried out on any predictive model. Okay, so let's stick with these model agnostic explanations and see what kind of explanations we can have. So we can divide them into two groups: global explanations and local explanations. And global explanations are focused on looking at the model from the perspective of the whole data set. We'll go back to this in a minute. And local explanations allows us to explain a model from the perspective of one observation, from the prediction for example, for one client. So in global explanations, so that are from the perspective of the whole data set, we can, for example, look at model parts, which means we are focused on the impact of variables or groups of variables on the model performance. Here are examples of methods such as, for example, permutational feature importance or local. But we might also be interested in other aspects of a model, for example, profiles. It is a model profile type of explanations. It aims at presenting how a variable affects the model response. So if we change the variable, how the mean response of the model would change. And here examples are partial dependence profiles and also accumulated local effects. And the third group, model diagnostics. These explanations can be used to evaluate the performance of a model. So there are all kinds of residual plots, but also fairness validation. So for example, some methods to assess the fairness of the model, for example, demographic parity methods. Okay, and for local explanations, we are interested in explaining what drives model predictions for one particular observation. As I said, for one particular client or a patient. So the most common ways to explain predictions are predict parts methods that shows the impact of variables on the final prediction for a particular observation. So for a client, that might be her or his age or gender or something else. And here people use methods like breakdown, like SHAP or LIME. We can also would like to see for the profiles for an observation. So the type of explanations here are predict profiles. Sometimes they are called sensitivity analysis, and it is similar to the model profile, but these profiles are not aggregated over the whole data set like in a model profile, but we rather profile the prediction from the perspective of a single observation. Yeah, so here examples are ceteris paribus profiles, or also known as individual conditional expectations. Okay, and the last one are predict diagnostics explanations. Here we evaluate the model from the perspective of a single observation. So, for example, we may look at an observation and its neighbors and compare the density of residuals for the observation and its neighborhood with the density of residuals for the whole data set.
Okay, so as Alicia has mentioned, we've dig through a lot of R packages for XAI, and today we would like to show you 5 of them we consider hot. And by hot, we mean that they either outstand other packages in the specific areas, so they perform things that no one package can do better, or they implement new things that were never met before in R, new conceptions for R in XAI, or third category is that they answer XAI issues that are important for that field of science. And today we are going to talk about 5 packages, which are DalExtra, Flashlight, Model Studio, Triplet, and VIP. To begin with DalExtra, it's an extension for Dalek package. Probably most of you are familiar with Dalek, which is a combined tool for XAI in R. And DalExtra as an extension provides mostly model diagnostics methods, including funnel plot that can be seen on the right. And this type of plot allows to detect areas of domain crucial for model behavior, and by that judge which model is better out of 2. And also DalExtra provides other methods to that help us distinguish best model for the current appliance. But what makes DalExtra really hot is that its integration with various machine learning frameworks, including MLR, MLR3, Carrot, Tidy models, Parsnip, and H2O, which, by the way, got removed from CRAN today due to policy violation. But also, DalExtra allows us to integrate with Python by giving a way to customize in a smoothly customize Python R connections via Articulate, and thanks to that, assess scikit-learn and Keras models. No other XAI in R can do it. Next package is Flashlight. Flashlight is a big combined package for XAI, meaning that it implements a lot of different explanations methods, and they are typed on the slide. As you can see on the right side, the plots in this package are quite nice. Also, it allows us to explain 2 models at once, which save a lot of time, and also allows us to compare explanations of 2 models very easily without additional effort. But what really makes Flashlight hot is wave use case, meaning that whenever we make explanation, whenever we explain the model, we can make computations taking into consideration waves of each observation, which can be very useful in, for example, scoring bank systems. And once again, no such feature in DalExtra, IML, or any other R package for XAI. Third package for today is Model Studio. And Model Studio represents a trend we believe that will be viral for R in the future, which is creating flexible standalone interfaces to assessing model explanations. As you can see on the GIF on the right side, using Model Studio, the user is able to navigate over different types of explanations at the same time, meaning that it's possible to explore whenever you want, whenever part of the model you want at any time. And because it's created once and then it's standalone HTML page or even applications for other packages. Big thing is that assessing those explanations does not require any specific domain, specific domain knowledge, or even fluency in programming, meaning it can be, for example, used by the people of business. Fourth package is Triplet, and we included Triplet on that list because it answers viral XAI issues, which are correlated features. And as you may know, model agnostic post hoc explanations does not really like with correlated features. Some of the results may be even meaningless if the correlated features are met in the dataset. That's why it's important to answer that issue, and Triplet does it. It introduced the concept of aspects, and aspects are a group of dependent variables that are considered as one variable. Example can be seen on the right side, where it's aspect importance for the Titanic dataset, and here the wealth, we have wealth variable that is a group of class and fair variables that are highly correlated. And instead of 2 highly correlated features, we can one aspect that acts as one variable, removing the issue of correlated features in the dataset. And what's even more amazing is that approach for local and global explanations. And last package for today is VIP package. that is mainly focused on the feature importance. I mean, it's only provides different feature important interfaces, but the power of the package lies in flexibility. It provides three crucial model agnostic methods for computing feature importance, which is permutational, Shapley, and variance-based feature importances. But what really makes it hot and distinguished among other packages for R packages for XAI that also can compute feature importances, it's the mix of model agnostic and model specific methods. Whenever we compute explanations with a VIB package, we can either choose to use one of the three model agnostic methods or the model specific methods, a method that's implemented for a specific type of models. And a lot of models are supported in the package, or different structured models are supported in that package, allowing us to compute feature importance based on the structure of the model. And to conclude, there are a lot of R packages for XAI, and all of them have different functionalities. There is simply no way to choose to point out one tool that will be good for everyone. That's why we, our users, have to try by ourselves and test which tool will be best for us. Today we've presented just 5, but there is a lot of more. We encourage you to visit a landing page for our article to see the preprint that will be available under the red link tomorrow. And there you will see 27 R packages and 6 Python libraries and comparison of them. Thank you for your attention.
Perfect. Thanks a lot, Alicia and Shimon. It was quite cool, and to have an insight about XAI packages, that was great. Okay, let's move on our next speech, and which will be given by Jacek Leskov, who is from Krakow Technical University, and is gonna talk about artificial intelligence, big data, and R. Jacek, stage is yours. Wish you good luck.
Thank you. I'm really pleased to have the opportunity to address this community. Let me only work on my sharing screen device to share what I have for you guys for today. Yes, I would like to address the sort of a general issue, how the artificial intelligence, big data, and R are working together. My presentation will be maybe more example-oriented, and whenever I'm going to move to more, let's say, general statements, I will be using the language of math, which of course is supported by R. So that's why the subtitle of my talk is How Solid Math Can Help Build well, the XAI models. Let me now move to my first part of the presentation, which is in PowerPoint, which is the first motivating example. Can you see well the running person on your screens? So I hope it is the case. Unfortunately, the PowerPoint presentation doesn't allow me to magnify it. Maybe I can do better.
Yeah, we can just see right now your presentation on me.
Yes. Oh, okay. Let me switch back to. Okay. Unfortunately, it looks like it wasn't a successful trial. So let me move to another example that I have prepared of the signal I would like to show you. So in my work career, besides doing the data analysis, I was working also with engineers to do the reliability and checkup of various mechanical systems. And the signal we were analyzing was the engine signal that you see here. And sort of a crucial part when you are analyzing the reliability of a mechanical system is the acceleration of the wheel bearing And, essentially speaking, you may have these days 50 sensors attached to a, for example, huge engine system, like in a big machines, like excavating machines. Each of the 50 sensors will be analyzing the data with at least the 10 kilohertz frequency, which means after several minutes, you will have millions of data to analyze. Now, what does it mean to do this type of analysis? Well, certainly, one of the major features that engineers are looking for when analyzing the properly working systems is the sort of a frequency plane. At the bottom left corner of this picture, you see the frequency plane, which is generating the autocovariant structure. And from this shape, you can guess whether the system works properly or not. Now, when you are moving to a system that doesn't work properly, and you also have the 50 sensors providing you with millions of data, you may see other shapes, and those shapes, the differences between those shapes may actually tell you whether your system is still working properly, or actually it moved to a not proper type of a mode. So in a classical setup, in the upper left corner of the picture, you are seeing so-called frequency signature of such a system. And the little red segment that is sticking away from the zero line is exactly telling you where is the frequency that is corresponding to a significant feature of a signal. So now, for similar pictures at the end of my talk, I would like to show other examples. Essentially speaking, the big data problem, the several millions of data problems, can be reduced using contemporary data analysis to just few components. And I'm going to show you in sort of a more or less mathematical way how to do it. When we are doing data analysis these days with advanced statistical models, we are saying that, especially for big data, for high frequency data, you can think of data as curves. So when you would like to analyze curves, you would like to choose an appropriate environment to this curve analysis. And in a modern statistical inference language, a very popular choice is to work with the curves that are represented by a Hilbert space, the curly H here, or to those of you who are maybe less math literate, this will be a space of functions integrable on some interval. We would like to have models. How to model curves? Well, we can use matrices, of course, but matrices need to be specified in terms of their dimensions. In modern mathematical languages, instead of matrices, we can use functionals. I'm not going to bore you to death with mathematical details. What you are seeing as equation 1, to those of you who have some previous background on a time series, this model looks suspiciously similar to the autoregressive model. And essentially, this is a type of autoregressive model, but now written between curves and not between just data points of fixed dimensionality. One of the main things is to be able to estimate such a model. So when you are working with curves, you need also to work with the estimating procedures that are able to handle curves. And due to the functional data analysis package in R, we are able to do that. And well, the formula 2 and 3 that you are seeing on your screens may look a little bit mathematically difficult, but they only show you sort of a general part of the story. That is how a curve can be decomposed into few functions which are driven by data, and we will be calling those functions empirical eigenfunctions. And then how those data can be decomposed into just numbers that we will be calling those numbers eigen numbers, and those are the empirical eigenvalues. So you have the theta hat and the lambda hat as sort of a drivers of a system of the estimating equation. Of course, when you are doing statistical analysis, you need to check whether your analysis is proper. That is, you need to have what is known in statistics as consistency. That is, given a large data set, you would like to be close to your unknown values. And this is the first block of my transparency. The second block is our ability to do testing. And you aren't able to do testing if you don't know what is the spread of your estimator. And we are able to show that those empirical eigenvalues, well, have a certain form of a spread that can be described with the normal distribution. Once you are past that point, you can do bootstrapping. Bootstrapping, as probably most of you know, those who are do data analysis, is one of a very popular way to establish confidence intervals. So, you know, in the second part of my presentation, well, I'll be moving to practical application of the bootstrapping procedure. Let me go back now to the description of the data. And again, due to my previous research with engineering and machines, I'll be in a very particular way analyzing 10 seconds of a signal, acceleration signal generated by the wheel bearing. The frequency here is 2.5 kilohertz, so which means 10 seconds already generates well over 20,000 data points. And we will be doing this functional data analysis. Instead of working with a high value, high frequency, let's say signal or time series, I can show you how to reduce the complexity to just few eigenvalues and eigenfunctions. First of all, according to the, this would be related to the nature of experiment, the segmentation. This part of the data analysis is segmentation according to the natural cyclical nature of the data. So you have, instead of one curve, you have here 15 types of curves to which we are going to do the functional data analysis. And we will be doing the functional autoregressive model in the periodical setup. That's why the acronym is PFAR, and the complexity of the model is order 1. That's why there is a 1 in the parentheses. We are able, with the functional data analysis procedure, to actually provide the eigenvalues here. We are able to provide the confidence intervals for those eigenvalues. And on the right-hand side, the most exciting part of this calculation is the coefficient called CPV, which is really the cumulative percentage of variance. You can see that only with FUX, essentially with the 6 eigenvalues, which have the corresponding 6 eigenfunctions, we are able to describe as much as 84% of the variability of the signal, which really is a big gain. So now, what does it mean? Well, how you visualize it in R. In R, you can see the correctness of your model in the following way. Look at this matrix with, let's say, 6 rows and 6 columns. On the diagonal, you have the eigenfunctions, which reconstruct the signal. And the beyond diagonal, you have correlations of scores, that is, projections onto the space generated by those eigenfunctions. This is like a modern diagnostics, very similar to a regression model diagnostics. If the choice of your variable, in this case, eigenfunction, is correct, your correlations should be very, very small. And actually, in this case, it happens to be what we want. And then, you know, we can do reconstruction. We were plotting together with my PhD students a reconstruction of the signal with the eigenfunctions and eigenvalues created by the functional data analysis module in R. And the red line is the synthetic signal, the reconstructed signal, and the black line is the original data line. Well, in my opinion, it looks pretty good for only 6 values that are available. And a similar picture is for the second group. You see slightly different eigenfunctions on the diagonal, but the most exciting is this picture of reconstruction. That is, we are able to capture those important features of the signal. And also the same happened with the third group. To change a little bit the nature of the data, but with the similar tool, I'm going to move to the very different data set. This is a time series of PM10, the particulate matter 10 element of the environment pollution in Sao Paulo in Brazil, measured in the hourly way. And we have applied an identical methodology with the functional data analysis. The question number one was how many eigenfunctions? In the previous example, it was 6. And here with the 6 eigenvalues, we were able to reconstruct well above 80% of the variability. And now I can show you the original data and the reconstructed data using our technology. So anyway, this is the list of the references. I would like to thank all the audience and my PhD students who are helping me with this picture, especially my warm thanks go to Adriana Michalik, who was helping me with the climate data. The FDA package in R and the good knowledge of the data provides you, first of all, an ability to reduce your huge millions of data problem to few eigenvalues and eigenfunctions. I have very good message also to one of the speakers of our session that also the FDA can handle spatial data. So if you have several generating points scattered across space and each point generates your time series, this type of thinking is very well applicable. What can you get from it from the engineering or climate point of view? Of course, you can do online monitoring based on the very reduced scale model. You have explainable model because those eigenvalues are strictly related to features of the signal. And then, as I mentioned during my presentation, the package FDI is available in R. We are probably going to add this PFAR package in the future. Thank you very much for your attention. And if you have any comments, I'll be more than happy to answer your questions at JLS-PK-EDU-PL. Thank you.
Perfect. Thank you so much for this great presentation. It was really interesting to see real-life applications. Okay, so now we are moving on to our last speech from this session. So, which is going to be what is new in DrWhy.AI, and it's gonna be presented by Hubert Baniecki and co-authored by Przemysław Biesek. And so, stage is yours, Hubert. Wish you good luck.
Do you hear me?
Yes, I can hear you. Yes, we can hear you. And we can also see your screen.
Okay, great. So glad to be here. Yesterday, there were many discussions about model validation and reproducibility. Also, I really liked the Frank Harrell's keynote that tackled on irresponsible machine learning practitioners or irresponsibly made models. So here we are to continue the story. So actually, the main role in this presentation is played by the DrWhy.AI universe. It's a collection of R packages for explainable AI, or interpretable machine learning, as some might say. Moreover, it now becomes a collection of tools and resources for responsible machine learning. The main package, DALEX, serves as an adapter for machine learning models and frameworks so that they are presented in a unified way for other packages to use them to produce the explanations and, of course, the visualizations of these explanations. There is an easy to remember link to our GitHub if you want to dive deeper. It's DrWhy.AI. So I am the contributor and maintainer of DrWhy.AI universe. And the important note is that I will be presenting mostly the work of my colleagues from the lab, which I am really excited about. And the main aim of this presentation is to find a useful tool or maybe helpful resource that you could use in your work with machine learning models. So here we have a quick spoiler, what's actually new. We have a new book, 3 fantastic tools that I will be talking about today. Also 3 new model explanations. We started a blog about responsible machine learning. And also in the end, I will try to answer the question of the conference, why R, right? Maybe Python. So first, the great step to start your journey in explaining predictive models is a book by Przemysław Biecek and Tomasz Burzykowski, Explanatory Model Analysis. It's available under this URL. So there are many model agnostic explanations discussed for local explanations and global explanations on the tabular data. This book really has it all, mainly the theoretical introduction to the explanations, but also code examples in R and Python. And I am really excited about this book because apart from the theory and practice, it also gives a great intuition when you try to gain knowledge on this topic. So the first R package created in our lab this year that I would like to highlight is the Arena R package. It could really make a lot of good for you when explaining machine learning predictive models, especially comparing multiple models. So what this package does is it creates a dashboard for explanatory model analysis, this advanced dashboard that can be used to compare multiple models and also trained on multiple data sets. So the package basically computates all of the explanations for you. It requires like 5 lines of code, and then you are presented with this dashboard that you can use to explore many model agnostic explanations, many data exploration visualizations. You can explore multiple observations, variables, and the data set, as I said. And the key trait of this dashboard is that it can be also serverless. So you can just save it as an HTML file and add it as a supplementary resource to your research or maybe in your company to your model, or just send it with an email, maybe, I don't know, versionize your models on GitHub with such dashboards. So this tool is fantastic if you don't want waste time on coding the explanations and you want to focus on the interactive model and data explanation. So the next R package is the Fair Models package. So model fairness, model bias has become a hot topic nowadays. Governments talk about some guidelines, laws, and regulations on the AI. But also the companies try to present their policies on data privacy, model accountability, overall responsible AI. So here we have our answer to this precise problem. It's the Fair Models package. It is a flexible tool for bias detection, visualization, and mitigation. So we can check many model fairness measures in respect to sensitive categorical variables. Maybe it's gender, maybe it's race. And of course, this package uses the DALEX explainer to compute its metrics. It has a lot of plots available for you. And also it has the techniques for pre-modeling and post-modeling bias mitigation. So if you see that your model is biased, you can try to change that. To fix that. Also, the one functionality that I really like is that you don't really need to check for bias on the variable that was used in the modeling. Actually, when you produce a model that doesn't use your protected variable, you can then add it to the check. And even if you don't use this variable in your modeling, you can still see if your model is biased because it has seen some correlation in your data. So the more niche package, but quite exciting for me, is the XAI to Cloud R package. It basically automates the process of deploying model explainers into the cloud. So if you are someone like me that never came around to learning some cloud tools, this package is really for you. What we have done is that you can basically easily deploy the explainer object from the DALX package into the DigitalOcean's cloud, and then you are presented with an REST API for this explainer, and you can compute model explanations in the cloud and just retrieve the results, the plots. This package can be really useful if you are doing a lot of computation, maybe it's Shapley values or some high dimensional feature importance that takes really hours to compute. So this package makes your life easier when trying to maximize your effectiveness. For me, it took like 10 or 15 minutes to set it up the first time. And after that, I was easily able to send my explainer into the cloud and compute my explanations there. So now coming into some single model explanation packages. So the first package is the Vivo package, which implements another way of calculating the variable importance. The measure is based on the ceteris paribus profiles for the local variable importance, but also we have now implemented the global variable importance, which is based on the partial dependence profiles. So the main idea is to somehow measure the change rate in the profile, because like intuitively speaking, the larger influence of an explanatory variable on prediction, the larger the deviation along the profile. So if the profile is flat or close to flat, we can say, we can argue that it's an important variable. So the intuition stays the same for local and global variable importance. It's just the change of the ceteris paribus to partial dependence. Of course, there are many ways of calculating the deviation, the area under and above the curve. So there are a lot of parameters in this package that you can customize to your needs. So it's a common these days to have a lot of variables when doing machine learning. So as my colleagues before were talking about the triplet package in their presentation, I really think that you should check it out. It was the first presentation in this panel. So when we have a lot of variables and a lot of correlated variables, we want basically group them into the aspects, we call them aspects somehow, to calculate the joint importance of these groups of correlated variables. And in this specific package, this grouping, automatic grouping, is done by hierarchical clustering of their correlations. So if you have a lot of variables in your dataset and they are highly correlated in some groups, then this package will automatically group them at any given cutoff that you pass to the explanation, and then you can produce your grouped variable importance. Last explanation that I want to introduce is the TreeSharp package, which is currently in the beta phase. So it's a fast C++ implementation of sharp values for tree ensemble models. We now support the most popular for us packages like EasyBoost and Ranger. We would like you to propose more if you want more models to be compatible with this package. And it also gives you global and local explanations plots. It's not currently on CRAN, but I hope that it will be in the near future. So hop on GitHub and give it a try. So some of the packages that I am presenting are introduced in the new Responsible ML blog that we have started. It's at medium.com/responsibleml. There are news, guides, examples written by the package authors, my colleagues in the lab. And hopefully there will be much more of these blogs in the near future. I really think that I really hope that you will follow this blog if you are interested in responsible machine learning or news about the DrWhy.AI family. So last but not least, answering the conference question, why R? So after the success of the R-DALX package, we decided to develop the Python package, which is currently already on the PIP. So for us, it's a complete toolkit for explanation of machine learning predictive models, meaning classification and regression models in Python. the pipeline is pretty simple. So given the model and data, you provide them to the main explainer class object. And then when this explainer is created, you can use many methods to produce model explanations. And these methods are most of the methods implemented in the R package, but also some more. Like we also wrapped around, we also made a wrapper for SHAP and Lime packages in Python. So the idea is to unify the whole interface for the user, so everything is the most efficient. Each method will return you an explanation object, and these explanations vary, but all of them have the same one attribute and one method, which is the result attribute, which is a pandas data frame with computed explanation, and the plot method, which uses plotly to visualize the explanation. So we decided to use pandas mostly in this package, as we think that it has more use in the explanation world when we care about the feature types and feature names and etc. So this package currently supports scikit-learn, but TensorFlow, Keras, XGBoost, LightGBM, but also but you can of course explain any machine learning model really, I'm glad that the Python community of machine learning is so nice that new packages that produce models are compliant with the scikit-learn API. So if any model is compliant with scikit API, it will be working with this package really well. In the future, I can announce that we plan to add the fairness module based on the fair models package that I presented today, and also the arena module for the dashboard interactive exploration based on the arena R package. So I hope that you have found some useful tool or resource. If not, then maybe you will share these packages with your colleagues. Finally, all of you can contribute, and the best way to do so is going on GitHub and creating an issue with a feature request or bug report.
All right, so perfect, Hubert. Thanks a lot for this great presentation. And it's great to see that a lot of things are happening in the domain of explainable AI. Okay, so this was the last presentation from today, and I really enjoyed, to be honest, and I would like to especially thank all of those speakers who gave presentation today, and it was a great honor to be with you here, and I learned a lot of things, and I was also curious about a couple of things, and I paid a lot of attention. I hope our audience also enjoyed a lot, and I would like to thank you once again, and I would like to also thank our audience to be with us, to support us, to view videos, and yeah, that was great to be here. And you can still, just a quick reminder about our audience, and our keynote speech just started maybe 30 seconds ago. You can directly go to the link on our YouTube page and then watch our keynote speech, which will be given by Kosha Bogdan. And you can still ask your questions using our Slack group. And thanks a lot, and have a great Sunday, and then have a great rest of our conference.
Thanks.
Bye-bye.